Okay.
So our stage of seminar this week are here in Dr. Montanga, and he'll be presenting and discussing environmental analytics, design management, analysis, and visualization of ecological data. So with that, I'm going to hand it over to Paul. If you have any questions, are you open to questions as you go?
Sure, absolutely. Anytime. So can I start with a story? I'll never forget finishing my master's thesis and having not a single clue what to do with any of the data because I had never taken a stat course in my entire life. And it left me very, let's say, curious about, what do you do with this stuff? And if you think about it, it's kind of silly because here we are in the business of collecting data, but not necessarily learning how to analyze data or how to manage data. And so when I went back to school for a PhD, I decided, in one way I was very lucky. The program I entered, I was required to take 8 classes, but there were no core courses or required courses. So I can take whatever I want. And so during my PhD studies, I actually took 7 classes in the math department. I only took 1 in the biology department. I've got a degree in biology. I always say I'm not a biologist, even though I have a degree in biology. And that's where I really learned how to do, let's say, statistics per se. The rest of the stuff I'm going to talk about is things I learned later on, much later on, in fact. Probably didn't learn most of this stuff until 15, 20 years into being a professor. But the reality is today we don't talk about statistics per se anymore. Today we talk about analytics. And what we mean by analytics is essentially the end-to-end process. So, whoops, how about that? So I'll get to the end-to-end process is what I mean by this bullet down here. It's really all about designing your work so that you're thinking about what it's going to look like at the end, and that you follow this logical progression to get from starting your research to actually ending with something that's a visualization that has some impact. And by impact, I mean a clear understanding. People clearly understand what it is you've discovered, what you're trying to present. The one thing I've learned in my long career is that the classic, 1 year of statistics courses is not enough. Most of you have probably taken math. I think it's either 63 or 53-15 and then 53-16. And all you really learn to that point is a little bit about normal distributions and ANOVA. And believe me, you haven't even scratched the surface of the things you need to know. And the bottom line is there's probably too much stuff to be covered, even if, you were doing a complete master's degree on statistics, for example. But again, today I think of this whole topic as being more, it's about being something larger than just the statistical analysis part itself. And in fact, if you look at my little logical sequence here, analysis is only 1, 2, 3, 4, 5, 6. It's only one of 6 steps, right? It's only one of 6 steps to get you to that finished product. So one of the things I've said to a lot of students in the past as they're designing a thesis or a dissertation or even a single experiment is think about what the end is. When you're done, what do you want to be able to show people that makes your point? And then try and work your way backwards to get to that level. So for example, in the lab I run, we do a lot of field measurements, a lot of field sampling. And so what we have is we got a whole bunch of pieces of paper with, pencil scribblings on it, okay? So how does one get from that, from those pencil scribblings, to this thing on the right? Well, it's my right. Is it your right too? Yes, it is. So the thing on the right is actually a figure from a manuscript. And that figure has a whole bunch of stuff on it. The top panel is salinity. The bottom panel is, the next panel is the flow rates. So salinity is sort of a chemical water quality measurement, right? And the daily flow rates is kind of a hydrological measurement that comes from a flow gauge. And also notice how I've put bands in there. How when the pass, this is actually the Rio Grande River, the mouth of the Rio Grande River, when it's open and closed. And then on the bottom, it's diversity of the invertebrates that live in the sediments there, and how that's changing with respect to these things. So this illustrates another important point, which is so much of what we do today is both interdisciplinary and integrated. And what you're going to need to do is be able to put all these various parts together, and your data sets are almost always multivariate, meaning you've measured more than one thing. And so we also have to understand that, we're getting back to the inadequacy of just 1 year's worth of statistics. It's almost all univariate statistics. It's almost always just one Y. But we live in a much more complicated world. And I don't think I know a single biologist, particularly an ecologist, who is measuring just one thing in their entire life. We're always measuring lots of things and trying to look for the patterns and relationships amongst the variables. And so the real question is, how do you get from handwritten notes on the left to a finished visualized product on the right? And that's what I mean by it's a complicated series of steps, and you actually have to become skilled in every single one of them. So the first part should be obvious. Well, we start with questions, we design. We're kind of up to the acquisition phase here, right? So the next very step has got to be data management, right? We can't analyze numbers that are handwritten on a piece of paper. Even if you're typing your data into an Excel spreadsheet, Excel is not an analytics medium. It's simply a storage tool and nothing more. Please don't do your analytics within Excel. It'll get you in trouble. And I can talk for hours about how you get in trouble with Excel, but that's another topic. So the bottom line is we typically start with questions or hypotheses. We start with a theory. The most important thing is understanding your assumptions. And I think this is probably the hardest part, particularly for beginning students, for a simple reason. You don't know what you don't know. You don't know where the pitfalls are. You walk into a lab, your professor says, okay, go run these samples on that machine. You're just assuming that all the numbers coming out of that machine are correct, right? You're assuming someone else has figured all that out for you. None of that's actually true, by the way. You have to really analyze the assumptions in all your data in all the steps of data collection. And you need to test them. You need to make sure that the data you're collecting is actually something you can believe and it's something real. You understand where error comes from, how it's introduced. The most important part too is using what I would call logic. And this is the issue of deduction versus induction. Boy, that's an hour-long conversation in itself as well. So actually, by the way, I used to teach this course called experimental design. It was a CMSS course. I taught it for I don't know, 15, 18 years. And then I kind of gave it over to someone else one year when I had to spend the spring in the hospital, and I never got it back. But every single slide here would be like a whole week or 2 weeks of a lecture in that course. So I'm kind of abbreviating things rather dramatically. Bottom line is you develop your questions, and one of the other tricky things is you got to make sure they're answerable questions. You got to frame your questions in ways where you can actually nullify the hypothesis. So when we get to actually designing experiments, there are a lot of key terms. And one of the things that always drives me nuts is how most people completely misuse all of these terms, nearly all of the time. But the bottom line is, so what I'm telling you here is the statistical jargon definitions. So right, all scientific fields have their jargon, and statistics has its own jargon. And it turns out a lot of people misuse these words a lot. For example, population. A population is it's a set of measurements, okay? And a sample is a subset. It makes a really big difference whether we're dealing with everything that can be measured or a sample of what can be measured. And a random sample is, every sample is of a similar size, but it's from that population. And here's the key thing: it has an equal probability of being selected. Now, the next thing you always learn in Stat 101 is all about distributions. Well, you know, and the line you hear all the time is this: your sample has to be selected from a normal distribution, or you can't use parametric statistics. That's the least of your worries. Your biggest worries is always that third bullet. Are you actually taking a random sample? And what does it mean? It means every single measurement has an equal probability of being selected. That's the real key. It really doesn't matter what the underlying distribution is. That's easy to solve. That's what transformations are for. It's absurd to think you can't use parametric statistics because of an underlying distribution. We can manipulate curves very easily, and I'll show you how to do that. That's not a problem. The real problem is, are you actually sampling correctly? How do you actually set up your experimental design correctly? That's what you really need to worry about. And then my favorite word, or I should say my favorite word to hate, parameter. A parameter is a number that summarizes the data of a population. For example, the mean of a population is a parameter. It drives me nuts. Chemists do this all the time. For some reason, they always call measuring, you know, like salinity, temperature, and dissolved oxygen parameters. Those are not parameters, those are variables. If you're lucky and you're doing things correctly, they're random variables. But I see people misuse the word parameter all the time. What is a parameter? It's a summary of your population. You take your whole population, you're going to describe it in one number. That's what a parameter is. And statistic is, again, it's a number and it's a summary of a sample. And it's always going to be a subset of the entire sample. So this, and an example of this is the sample mean. Now notice I distinguish between population means, which are mu, and sample variable means, which are y bar. And again, this is pretty much the only thing you really learn usually in Stat 101 in that first whole semester, is the difference between population means and sample means. But somehow we forget it. We forget the implications of why those things are important. So keep it in the top of your mind when you're designing experiments. So one of the things I always like to do when we talk about experimental design, we're still on the design phase of it, is talk about the general model. This is probably one of the most powerful constructs from the early 1900s was realizing we could describe every single experiment on Earth with a simple general model. And that model is real simple, y equals x, plus some random error. Now the trick is, there can be many y's and there could be many x's. It doesn't really matter. So all we have to do is put brackets around y and x, and now we've defined every single experiment on Earth with that real simple thing. And if you understand the principles of deploying the general linear model, you can't go wrong. Now, some people will get all upset and say, well, some processes are not linear. I know that, but it doesn't really change anything. It doesn't really matter whether our x's are additive or multiplicative. We can deal with it. It's just a matter of getting your models correct. The important thing is the stuff on the left of the equal sign are what we call dependent variables, things that we measure, and the things on the right of the equal sign are called independent variables. These are things you should be controlling. There's something else really important about this simple construct. It tells you how to write a method statement in a paper. I always tell people the first thing you should do is have a paragraph about the overall y equal x concept. The second thing you do is you have a paragraph on all your x's. And the third thing you do is you talk about your y's and get into the details of how y's are measured. And hopefully, just by presenting it this way, it should be obvious to you why I think it needs to be in that linear construct. But the bottom line is, a lot of times, there are many different things you could have measured. You just chose one. The worst thing you can possibly do is start a methods section with the y variable, describing what you measured. You leave the reader with a simple question. Why are you telling me this? Why did you measure this? Did you just measure it because, as the old saying goes, when all you have is a hammer, everything looks like a nail? This is what you know how to measure, so that's all I want to talk about? And the rest of it doesn't matter? No, it should be the other way around. There should be a question. The question should lead to some kind of response. That's the first paragraph. And then the second paragraph is, how do we answer the question? Describe all of the x's. And the third paragraph is, describe the responses. How do we measure the y's? And again, as I said earlier, both x and y can be either univariate or multivariate. It really doesn't change anything according to the general nature of everything I'm describing here. So this is an example of a model with lots of x's. For example, you might have dates and stations, but it can be an infinite number of things you've measured. And then here's an example of a multivariate design where you've measured lots of different y's. But the linear, and of course it can be both on both sides. We can be multivariate. All right, so one of the things I always do when I'm trying to figure out how do I analyze a design is I draw a picture of it. I find pictures very useful. I'm hoping that's going to show up. Oh yeah, here we go. And then we build our mathematical relationships. So for example, here we have a treatment called A, and notice that they're all different, 1, 2, and 3. And then we have a treatment called B, and we notice they're the same. They're repeated underneath each one of the top level treatments. So in case you're not aware of it, this is what we call a classic nested design. And then you can also do things like this. You can build block diagrams for these kinds of things. But once you do this, it's pretty simple to convert that into a mathematical model, which is actually your statistical model, and it's really easy to analyze these things in whatever your favorite software package is. So the next line I just put up as an example of how most coding works. Most of the time we don't code things with our Greek letters and in a formal mathematical way. You'll notice two things here. Number one, almost all computer software that calculates ANOVA, you almost never explicitly mention the overall sample mean, nor the fact that you're calculating a error, which is the mean square error in all these things. This almost always gets left out. So I actually said something wrong before. I said the other one was nested. This is the nested one. Here, notice that B is unique in every single treatment above it. That's a nested design. And the block would look something like this. Notice that in a nested design, you have missing types. So for under treatment 2, under A2, notice that 1 and 2 don't exist and 5 and 6 don't exist. That's what we mean by unique and nested. And then there's all that stuff. Okay, next thing you have to always be concerned about, particularly if you do a lot of work with machines and you're getting your measurements out of machines. And that is the difference of accuracy versus precision. So accuracy is the closeness of measures to the true value. Precision is closeness of the measurements to one another. Typically, precision is an issue when you're using machine and maybe you send a sample through a machine 3 times and you don't necessarily get the exact same number out of the machine all 3 times. That's precision. But notice that in this example, the one on the right, all the darts are a lot closer together. So the precision is high, but also notice that the center of all those darts is way off to the left. It's nowhere near the center. Whereas on the left-hand side, the darts may be very far away from one another, but the average of all those locations is a lot closer to the center than the one on the right. So even though there's a lot more spread in the darts on the left, it's actually a more accurate measure of the true value, okay? So again, it's super important to always distinguish between accuracy and precision. And in particular, when we're making machine measurements, we want to have a measure of our precision of our measurements. In other words, you know, a real typical thing, and I don't know where this came from, but it's something I've been repeating for 40 years now. You know, it's always, if you're using a machine to collect data, it's always good to rerun 10% of your samples. Don't ask me where the 10% comes from. I can't tell you. I think it was something EPA came up with in the 70s. And, you know, that would give you an estimate, and then the variance amongst those machine replicates, that's a measure of your precision. You want to hear another funny story? So when I was an assistant professor, I was like there for a month maybe. And I was getting together with a senior faculty member who was a chemist. And we were designing to do a big study in Baffin Bay at the time. And I'll never forget starting to talk about replicates, going to a bunch of different stations and a bunch of different places. And he said to me, replicates, what do you need replicates for? We just measure it right the first time. What's the difference here? You know, he's talking about precision, I'm talking about accuracy, right? I wanted to make sure what we were measuring was representative of the whole Bay system. He was worried about, is the number coming out of my machine correct? That's a true story, by the way. And I don't think I even understood it at the time, but it's one of those things in retrospect I understand very well. So let's talk about ethics real quick. I shouldn't have to say this, but don't make stuff up. It's just that simple. Just don't do it. Don't make stuff up. It's just wrong, you know? And there's only one way to be able to prove what you've done is yours and it's real, and that's to have real strong quality assurance, quality control procedures in place. We also call this QA/QC sometimes. If you do environmental work, this is an absolute requirement. You can't defend values without proof that those values are valid. And you have to provide two kinds of proof. Number one, the assurance part is your machine working? This is where the precision things come in. Can you prove that the machine is giving you real numbers? And there's lots of ways, you know, for example, you might have a standard curve, for example, to demonstrate the validity of values coming out of your machine. Then the second thing is quality control. Now, for my lab, we're mostly focused on quality control. And that's where we actually inspect data. What we're talking about now is something real simple. It's proofreading. It's maintaining those original handwritten sheets and archiving in a permanent way and being able to prove that what was written down by that lab technician 10, 15, 20 years ago is exactly the number you see in my database today. And I also did a lot of work for the Deepwater Horizon oil spill many years ago. And I'll never forget when NOAA sent a team of 3 people to my lab to check all of our QA/QC procedures. They spent the whole week going over all of our work, trying to verify subsets of data, random parts of data. And I wasn't worried about it, and they found absolutely nothing out of place, because long ago I learned how to create very strong data management program that included a very strong QA/QC procedures. And so that has served me very well over the years. Now, let's talk about types of data real quick. Again, this is all in the realm of definitions. So there are 2 kinds of variables, continuous and discrete. Continuous variables are things that have fractions in them. Discrete variables are whole numbers. You can think of them that way. They have very different properties. They have very different needs to work with them in the context of data management. So those are your measurement variables. There's also the control variables, right? The X side of the equation. These can be either numeric or alphanumeric, meaning categorical, right? So for example, you can have treatment A, B, and C, or you can have a treatment where you expose something to different, let's say, nutrient levels. So A has 0.1 grams, and B has 0.2 grams, and C has 0.3 grams. So in that case, they're numeric rather than categorical. Now, one of the nasty details about data management is we can never mix these 2 in the same column. So if there needs to be notes about numeric information, you got to create a second column and keep your notes in that column. If you don't do that, you'll never be able to analyze the data set. And hopefully I'll have a good example of that in a minute. Here's another important thing. What's the difference between data and metadata? Who knows what metadata is? Anyone want to yell it out? I have the definition right there. You can read it. Data about the data. I can't get over how many times, even working with assistant and associate professors, they don't know the difference between that data and between metadata and ancillary data. So for example, if I go out and I only care about I typically study benthic invertebrates, but I always measure things like salinity, temperature, and dissolved oxygen. I've had some people say, oh, that's your metadata. No, it's not. That's ancillary data. That's data I won't necessarily use to do an analysis on the invertebrate data set, but it's data that may help me understand, the distribution or why we see the changes. But metadata is incredibly important, and it's one of the things nearly all students forget to include in their spreadsheets. So if you have a spreadsheet, and hopefully I have an example for you coming up, where you've got your rows and columns of data, you need a second spreadsheet, which is labeled metadata, that describes what every single column is. And good metadata will tell you the methods, the units, where was it collected? Oh my God, you'd be surprised how many people, particularly for field work, can't give you the latitude and longitude of where a sample was taken. That's unforgivable. Believe it or not, there are times when the time of day might be important, not just the date, but also the time. So include it all. Also, you need to know if there's derivations. Sometimes your data set has calculated values. You gotta know the difference between direct measurements and the calculated. Then there are the declarations. What do I mean by declarations? Well, sometimes you may have to have a permit to collect certain kind of data. You better have that written in your spreadsheet, because trust me, 6 months from now, you won't remember. So, oh yeah, I even wrote that. Make sure you write it down because you won't remember later. So, effective data management guarantees data is accurate, aligned with research objectives, and used to drive better decisions. What is that? That's QC, right? That's why we have strong data management protocols, because it ensures the quality control. All right, next topic, database structures. Turns out there's a lot of ways to put data in a spreadsheet, a lot of different ways. But in computer jargon now, we talk about two basic data structures, flat files and relational databases. So a flat file is usually simple, but it usually makes it difficult to keep all the data, the metadata around. And the other thing is, it has a tendency to be very repetitive, and it makes for bigger files, bigger and more unwieldy files. And so on the right side is an example of a flat file. And it's obviously, I'm only using very simple examples here. But for example, one of the things I commonly do is in my field work, I'll have sampling dates in different stations. So here we went out on March 14th. We sampled 3 stations, we measured salinity. And we have all the information in one place. But what is missing from this? Well, where is station A? That information is not here, is it? And imagine if we sampled replicates. Imagine if we sampled lots of things. Imagine if we sampled, if we had many variables. Let's say we had 20 or 30 things we measured. Would I have to write the latitude and longitude for A 20 or 30 times? It's exactly what you would have to do. Otherwise, the information will be lost forever. This is why relational databases were collected. In a relational database, you have a key variable, and then everything is based, and then you have different sheets in Excel terms or different files in computer science terms. And all you gotta do is match merge them based on the key. Keys can be very complex, meaning very long, or they can be very simple. So in this case, I just have 3 samples, and my keyword is sample, and it's 1, 2, 3. And in different sheets, I have the different data. And for example, in this particular case, maybe the easiest thing is on the flat file. If I just add a column there with 1, 2, 3 on another sheet, I can have a latitude and longitude one. So I don't have to match merge all of them all the time, but I have that information available. So in computer science language, when we merge things by that key variable, those are called joins. And there's a, again, when I give an hour-long lecture on this, I will explain the difference between inner joins, outer joins, and all that kind of crap. But if you ever work with SQL or any of the database management kinds of software, you kind of need to know that jargon. But there's a whole bunch of jargon related to these things as well. Now, database data that is well managed is in the right place at the right time in the right format, and it's for everybody. This is also called, and here's an example of how I do mine. I love to use Excel to store data and to share data with other people. And you'll notice that the first page here is called metadata. Let me see what the next file is. Oh, and so here is this sheet called data count. And so notice that what I have here is I define, I take all the column names and I make them rows, and I define them all, and I also add the units. And notice that rather than having a separate sheet for the locations, whoops, I just put them all on top sheet. That's probably a lousy way to do it, but it's fine. We can have a sheet called, in fact, that's probably what this one is over here, station. That's probably got all this stuff, all this kind of information a second time. But but I think this approach in general is something I strongly recommend. You'll also notice that I put a title, I put my name in it. I even put a little reference here. I put the purpose. You're gonna be amazed how easy it is to forget all this information. So particularly if your career spans more than 1 year. So I highly recommend you include all your metadata in every spreadsheet you ever create. There's another important thing. Notice there's no blank cells or fancy formatting. Notice that all the columns are homogeneous, meaning there's no columns that mix numbers and letters. That's all very, very important as well. Okay, next. So we're in a new world, and this is a change that has only occurred in the last 5 to 10 years. But just about every journal today, every good journal or journal of high quality, reputable journal, is requiring that if you submit them a paper, you have to have a statement about data availability. Now, we're not to the point yet where journals are requiring that you can't publish it unless you archive your data, but you at least have to make a statement. And a lot of people are making statements like it's available upon request. You know what the problem with that is? I don't believe it. I'm an editor of a journal. I see that all the time. I don't believe it. And you want to know something? 3 years from now, I'll bet that person will never be able to find that data or give it to you in a reasonable way. So I know that's BS. I know the days of data available upon request, those days are numbered. I don't know when it's going to change. I don't have a crystal ball, but I can guarantee you it will someday, and probably sooner than later. So there's this thing called FAIR. FAIR stands for findable, accessible, interoperable, and reusable. It should be clear to you, well, findable means, can you find it? Accessible means, what is the format? This is why people love just plain ASCII files or spreadsheets today, because they're pretty universal. There'll probably always be, 100 years from now, I'll bet you'll still be able to open up an Excel file. And this is what interoperable means. It means it can be used in different systems. And reusable, that means the metadata is good. That means there's enough information about the data that someone could look at and figure out what the hell it is and how to use it. And there's a nice little website in gofair.org. I love this little website. Now, suppose you wanted to put your data somewhere. There are tons of places to put data, tons and tons. I'm going to highlight Grid C. And the reason is simple. Grid C is actually right here on campus. So it turns out Grid C, and I can't remember what the acronym stands for, by the way, something like Gulf Research Initiative, something, something. But Grid C was created during the Gulf of Mexico Research Initiative, which was funded with $500 million from BP. And they had a requirement. They had a requirement that all the data generated with their funding had to be available online, either at publication or within 12 months of collecting it. And if you didn't do that, they dropped you from funding. And a couple of big $20, $30 million programs literally got discontinued because their PIs weren't putting their data in a repository. And so there was a little competition to see who would build a depository, and HRI won it, and it's still going today. Today it's being used primarily by the other Center of Excellences, which are again funded by this oil spill money. But there's a lot of stuff in Grid C. I can't remember the details, but I'm sure if you looked at About Us, it'll tell you how many gigabytes or terabytes or whatever. So I practice what I preach. If you put my name into the search window, you can see I have 31 files in Grid C. I have a total of 45 archived data sets because I'd been archiving data way before Grid C ever came along. And I'm very proud of that, by the way. That means if I ever do retire, everything I will have ever created will be available for people in the future. And if you think about the fact that nearly all research is funded by public money one way or another, it's almost like criminal if you don't make that publicly available before you leave. Whether that's moving into a different industry where maybe you don't do this kind of work anymore, or retire, or die, or whatever. So I feel like it's my obligation before I die to make sure every single piece of data I've ever collected is online and available for everybody. So let's just, for grins, let's look at this first one right here, give you an example of what it looks like. And you'll notice it's got two buttons here, data set and available. Data set means that it's been submitted, but not published yet. So what the folks at Grid C do is they basically put a data set through its paces and they see if it works. They see, is it fair? Can I actually figure out what this is and how to analyze it? Are there problems in any of the cells? Bad values, missing values, blah, blah, blah. Are there duplicated values? Are there undefined values? And once they put it through its paces and feel like, all right, this is ready for prime time, then they make it available then the available button will pop up and it'll be downloadable. And so here's an example if you clicked on that. The other thing that's super important about this is notice that you get a DOI. That's the first thing in FAIR, right? It's findable. It's got a digital object identifier. And it looks like 19 people have downloaded this. Isn't that something? It's been around since 2017 and only 19 people have downloaded it. I guess, I don't know if that's good or bad, but the bottom line is I'm quite happy that people are using this. And every once in a while I'll get an email and someone will ask me about a data set and I'll just give them the DOI. I don't have to send it to, I don't have to on request, I don't have to go out and create it or do anything special. Okay, we're ready for the analysis phase. So, Audrey, how am I doing on time? I need to be done in 12 minutes, did you say? Okay. I'm gonna go through this stuff. So, exploratory analysis, blah, blah, blah. Analysis of variance. Assumptions of ANOVA. The most important thing is this issue of linearity. Independence of error means that the samples are random. And then, of course, you've all probably seen this in Stat 101. I'm going to buzz by some of these things. Now, this I want to hang on for a minute or two. Again, as both a reviewer and an editor, I can't tell you, and as an author, I can't tell you how many times I've seen reviewers write sentences like, well, you can't use this analysis because this data is not normal. There are three things wrong with that sentence. The first and foremost one is it's not the data that's supposed to be normal. It's the residuals. It's the error. And so what does that mean? That means, right, we're back to the important assumption that the samples are independent. You've actually collected random independent samples. As long as that's true, you're fine with ANOVA. Don't let anyone tell you difference. But suppose your residuals do have a funny looking distribution. They're supposed to be bell-shaped, right? Suppose this bell is to the left, or if it's real skinny and real tall. Oh, as I said earlier, there's a hierarchy of things to worry about. And the first and most important thing is, are you actually using the correct model to describe your data? If you don't use the correct model, nothing that comes out of it's going to ever be right. That there'd be random sampling, homogeneity of variances is pretty important. But again, that's related to random sampling. It's pretty hard to break the rule for homogeneity of variances if you sample randomly and your samples are independent. Because what that means is that, you go to two places maybe, and they're not even in the same population. Again, jargon population term, part of the whole set of the world. What typically happens, again, which is incorrect, and which I see all the time, is people take 3 replicates at every site, and they find out, yeah, one site's got a lot of variance and one doesn't. And they think they violated this rule. No, you simply have a small sample size, right? We're back to the dart thing. If you throw 3 darts against the wall, the likelihood is 2 will be close together and 1 will be far away. That's just the way the world, that's just probability 101. So unless you take 30 samples, all of the tests for homogeneity and all of your software is all bullshit. It's just that simple. If you get a significant test for that, it's probably because your sample size is small, not because there's actually a violation there. So that's usually not a big problem. There's something else I learned. I told you I took a lot of stat courses. One of the courses I took was in non-parametric statistics. And I got this thing right. What we did in that course is we basically analyzed everything with parametric and non-parametric approaches. And then we did Monte Carlo simulations. And we also read about papers where people did that. And even when remember, what's the key assumption here? That everything has an equal opportunity of occurring. So imagine a uniform distribution. So imagine all the numbers from 1 to 99. Each number can occur only once. There's no way there's nothing that is less normal than a uniform distribution. And so when people do these simulations, they find out that ANOVA will give you the correct answer 9,000 and, basically 1 out of 10,000 times will you get it wrong anyway. So the point is that parametric statistics are very robust, even if you don't have a normal distribution. But if you really worry about that stuff, you know, we can do transformations. And in reality, there's something we call the transformation severity series. So here's a little table that tells you exactly which transformation to use, given different properties of data. And you know, you can use the most severe, which is presence and absence, right? Everything's a 0 or a 1. And so imagine this is your range of values in, you know, y to the 1. These are the sort of values you get when you use these different transformations. And you'll notice as you go to the right, you get further and further from the actual value. So if the actual value is 10,000, the root of that is 100. Log is 9. The fourth root is 10. Log to the base 10 is 4. And of course, presence and absence is the 1. But the bottom line is, we can always find a transformation, no matter how ugly your bell-shaped curve is. We can always find a transformation that'll, if you're really worried about these things, that'll work. It's just a matter of the severity. And one of the rules is you always want to use the least severe as possible. My favorite is always the root transform. A lot of people like log to the base e, the natural log. Log 10 is twice as severe. Notice you go from 0 to 9 rather than 0 to 4. But I like the square root. That's always been my favorite. And now on to my next little diatribe. We don't use the word significant anymore. I know you're still being taught the word significant in your stat classes, but you need to be aware that most research statisticians have been saying for about 20 years, been trying to convince their fellow stat professors to stop using the word significant. Why? Because 0.05 is an arbitrary value. Why not 0.04? Why not 0.06? Why not 0.1? R.A. Fisher in 1930 pulled 0.05 out of the back of his pocket and said, here's the number. That's why we use it. There is no valid reason for 0.05. You're simply saying, if I can make a mistake only 1 in 20 times, that's good enough for me. Fine. But the point is, we really don't need the word, okay? And, you know, think of some extreme examples like 0.51 versus 0.049. It's kind of silly. And we've even seen people try and do things like this, where they think that the amount of zeros in front of your number tells you something about how significant it is. So is this little box on the right correct or wrong? Take a wild guess. It's wrong. The p-value you get is a function of the sample you took. If you went out and took another sample tomorrow, you'd get a different p-value. Why? Because the sample, what's a sample? It's a subset of the population. If you choose different subsets of a population, you're always going to get different p-values. So, and again, it's like the example I told you about, if you throw 3 darts against the wall, the likelihood is 2 will be close together and 1 will be apart. That's what your p-value is doing. It's just telling you about the spread in the sample. So a p-value tells you only about the specific sample you took that day, nothing else. So it's basically, and it's also a binary decision, which is also probably incorrect most of the time. So we actually have a rule in my journal that you're not allowed to use the word significant. We actually tell people, you're not allowed to use that word. Now, what do you do instead? We want you to report the p-value, but we want you to focus on the effect size. Don't tell me I found more plankton at high tide than low tide. What is more? Well, I found significantly more plankton at high tide than low tide. What is wrong with that? It's completely vague. I don't know what more is. If you say, I found 50 at high tide and 25 at low tide, I understand that. And then if you want to tell me what the p-value is and also include the n, that means something to me. If I see an n like 3, I'm going to go, eh. But what if you said, I found 50 at high tide and 49 at low tide, and the p-value was 0.04? I'm probably not really going to, and the n was 3. I'm probably not going to believe it. Also, if you have an n of like 100 or 1,000, the p-values will always be 0.001 because it's a function of sample size. So when you have huge samples, the p-values tell you nothing as well. Everything is always significant in huge samples, or less than 0.05. So it doesn't mean anything. So the bottom line, guys, don't use the word significant. Don't use vague words like more, larger, greater. Tell people the effect size. Tell it's 10% larger. Isn't there a big difference between 1%, 10%, and 100% larger? Hell yes. Why wouldn't you tell people about that rather than hide it in a vague term like larger or greater? And and in fact, we were so adamant about this, I asked this friend of mine who's a statistician and does a lot of work. I told him, hey, can you write an article about this for me? And in January 2020, this was the first article we published in 2020. And it was when we instituted that new policy that we discourage the use of the word significant. We actually allow it if you insist, but we discourage it. And here are examples of how to say things. And I think these are examples from the Smith paper. So I'm going to jump ahead. Visualizations. Well, we're on the last bit, and I don't know, I can spend 2 hours just talking about this. I obviously don't have it, so I'm going to jump ahead a lot. Here's the main story. And I think when I told you, I gave you a lecture on publishing, I think I already went through all of this, so I can go through it quickly. It's got to be standalone, and you got to have good symbols. Your axis labels should always have the variable name and the units in parentheses. You'd be stunned. I would say half the papers I see don't have graphs that have the variable name and the units on it. And I think what I told you is, here's an example of the default settings. And then I created it in black and white. I made it a little bit better looking, and then I added color to make it all pop. I think I already gave you this example when I talked about things. But my point is this. Always go beyond the default settings. Always, and here's what it looked like in the journal. You'll notice the other thing I did here is I knew exactly, it's like 3.5 centimeters, I think. Is that right? I think so. The column width was like 3.5 centimeters. I just made sure that everything was going to be readable at that size. So you got to think about what it's going to look like on the printed page. And in PDFs, they might take up both columns, and that's fine. All right, I'm done. It's 12:30. I'm sorry I talk so much. Questions, comments, concerns? Yep.
Ethics. So if you don't collect your own data, just have to rely on those people that did process it. So like, I use data that's UCAR processed. And I just need to mention that UCAR processed it, so if there's a problem with it, it's their fault, not mine.
Right. Yeah, that's a declaration. And the other thing is you could always go on their website and look at what their QA/QC is. And you can even report about it. That's a good question though, because I do it all the time. I use other people's data as well. And if we're going to actually archive and make data fair, findable, and usable, it's going to be a more common practice. All right. We're done? Audrey, I'll turn it back over to you then. Sure, and I can share you this PowerPoint if you want. But yeah. Yes, if you need help with anything, like I told you, I'm also an editor for a journal. If you need help, you want me to look at a manuscript, in 10 minutes I can tell you whether it'll be, not whether it's acceptable or not, but whether or not it's ready to be sent to out for review. That I can tell you in 10 minutes. And if you need help with anything at all, feel free to call me. You know, it's easy to find me, paul.montagna@TAMUCC. Send me an email, no worries, anytime. Or you can ask her, she knows where I am. She's one of my partners in crime. All right.